Hi, welcome back to Physics Teacher, the channel that prepares you for the Waterloo Math and Science contest. This is the last question from the Euclid contest, and looking at this diagram, we have 5 circles of increasing radius, the smallest one in the center, surrounded by 2 larger ones in this order. And what we need to do is we need to figure out for all positive integers of c, for which this function f of c, which is defined as the number of pairs for a and b, is even. Give it a try, and I'll be right back with the solution. Alright, so what I'm going to start to do is connect all of the centers of the circles to form a quadrilateral. And inside that quadrilateral, we will have 4 triangles. And it looks like so. So we have our 4 triangles, and we can see that the edges of our quadrilateral are all a plus b, a plus b, a plus b, and a plus b. And for each triangle, let's look at this triangle for an example, POQ. And we can see that this side is a plus b. This side here is b plus c. And this side here is a plus c. And all triangles are identical, so all 4 triangles are congruent, meaning that this angle here is the same for all 4 triangles as you go all the way around. And we have 4 of those angles, here, 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 and here. So what that means is that angle, let's call it theta, 4 of those thetas will be equal to, as we go all the way around, 360 degrees. So theta is 90 degrees. So each of these 4 triangles is a right angle triangle, meaning we can analyze it with Pythagorean theorem. So we can take the hypotenuse, which is a plus b squared, is equal to the sum of the square of the sides. So we have a plus c squared plus b plus c squared. So let's expand this. So here we have 3 perfect squares here. So a squared plus 2ab plus b squared is going to equal a squared plus 2ac plus c squared. And finally, we have b squared plus 2bc plus c squared. Alright, so we can simplify this a bit. If we subtract both sides by a squared, these will cancel. We can do the same with b squared, like so. And we end up with 2ab equals 2ac plus 2bc. And then we have 2c squares here, so plus 2c squared. Dividing through by 2, we get ab equals to ac plus bc plus c squared. Alright, so I'm just going to rearrange for c squared. So I'm going to bring these terms to the left side of the equation. So we have a c squared on the right, and on the left we have ab minus ac minus bc. And then I'm also going to add a c squared to both sides of the equation. So if we look at it carefully, we have here, we can pull out an a, so we'll have a times b minus c. And over here, we can pull out a c, so we would have minus c times b minus c. And that'll equal 2c squared. So each of our factors had a b minus c. So we can continue to factor, and we will have a minus c times b minus c is going to equal 2c squared. Okay, so a couple of things we can learn from this is, 1, this is not a perfect squared. If you were to take the square root of that, you'd have root 2 times c, and root 2 is irrational, so that's not going to be a perfect squared, which means that these 2 factors are distinct. They're not the same. And we can also see that based on the fact that b is going to be bigger than a. We can also see that since both A and B are bigger than C, these are both going to be positive. So we have positive divisors here, or a pair of positive divisors. Now determining the value of FC is equivalent to counting the number of pairs of positive integers of A and B where this is true. Now every pair of A and B is going to correspond to a pair of positive divisors of 2c squared. So what we want to do then is to determine all positive integers c for which 2c squared has an even number of divisor pairs. Or put another way, 2c squared is going to be a multiple of 4. Why a multiple of 4? Because each pair of divisors corresponds to 2 divisors. And 2 times any even integer is going to be a multiple of 4. So let's start by breaking up c into its prime factorization. So that would be 2 times a certain number of multiples of 2 times our next prime number, let's call it just p1, times a certain number of p1s, let's call that to the power of x1, times p2 to the power of x2, all the way up to some unknown value pk to the power of xk. Right, where p's are our primes, and x's and r's and k's are all positive integers. So if I multiply both sides by 2c, we'll get then 2c squared is equal to 2 to the power of 2r plus 1 times by this prime number to the power of 2x1 times this next one, which is p2 to the power of 2x2, and so on all the way up to pk to the power of 2xk. So now we need to determine the number of divisors in this number here, 2c squared. So let's see, how do we do that? How do we find the number of divisors? Let's look at a simple example. It's called the number of divisors n. So let's say we had some prime factorization for a small number, say 2 squared times 3 squared. Well, that just equals 36. So how many numbers is 36 divisible by? Well, it's divisible by 1, 2, 3, 4, 6, 9, 12, 18, and 36. So it's divisible by 9 numbers. Well, this is an easier way to figure that out, especially for a large number like this. You can say n is just equal to that first exponent in our prime factorization, 2 plus 1, and the next exponent plus 1, and so on and so on and so on. So in this case, you can see 3 times 3 is 9. In this case, 2c squared is divisible by, so we have 2r plus 1, and we'll just add 1, so that's 2r plus 2, times by, so x1, and we'll add 1, or 2x1 plus 1, and then 2x2 plus 1, and so on and so on and so on, all the way up to 2xk plus 1. Now right here, you can see that all of these terms are odd. The only one that is even is the first one, which means that n can only be a multiple of 4 if this first term is a multiple of 4. So 2r plus 2 must be a multiple of 4. So let's set it equal to 4 times some positive integer s. And if you just rearrange that, you can figure out that r is equal to 2s minus 1. So r itself is going to be an odd number. So we can conclude by saying all positive integers c for which fc is even occurs when we have an odd number of factors of 2 in our prime factorization.